A Bloom filter answers a strange question. Can this item be definitely absent, or is it only possibly present? It never returns a trustworthy yes. That limitation is exactly what makes it useful. Imagine a venue with 1 million banned ticket codes. Checking the database for every arriving code is expensive, especially when almost every visitor is legitimate. Put a compact Bloom filter in front of it. When the filter proves a code is absent from the blocked list, skip that database lookup. If the answer is maybe, check the real database before making a decision. The structure is a bit array initialized to 0, plus several hash functions. Use a tiny example with 10 bits and 3 hashes. Insert the fruit pair. The 3 hash functions map pair to positions 1, 4, and 7, so those bits become 1. Now insert a plum. It maps to 2, 4, and 9. 4 was already set, the other 2 become 1. Next, check an apple. The apple maps to 0, 4, and 8. Bits 0 and 8 are still 0. Because even one required bit is 0, that apple was definitely never inserted. The filter can reject it immediately. Now check a grape. Suppose the grape maps to 1, 4, and 9. All 3 bits are 1, but the pear and plum set those bits earlier. The grape may never have been inserted. That is a false positive. Shared bits can make an absent item look possible. Why are there normally no false negatives? When an item is inserted, every position selected by its hashes is set to 1. A normal Bloom filter never clears individual bits, so a later query for that same item still finds all of them set. Deletion breaks that assumption because clearing a shared bit could erase evidence for another item. A counting Bloom filter replaces each bit with a small counter when controlled deletion is required. The false positive rate grows as the array fills. More bits reduce collisions but consume memory. More hash functions help at first, then become counterproductive because every insertion sets too many positions. Real implementations calculate the bit count and hash count from the expected number of items and the acceptable false positive rate. Here is the same logic written in code. To add a value, map each hash into the bit array and set the resulting positions. To query, calculate those same positions and return false if any one of them is 0. Return maybe only when every required position is 1. The filter must never be the source of truth. In a storage engine, it can avoid reading a disk table that definitely does not contain the key. In a web crawler, it can reduce duplicate URL checks. In a cache system, the filter can keep repeated misses from reaching the database. But when the answer is maybe, still check the authoritative store. Monitor the observed false positive rate and rebuild when the filter becomes too full or the underlying set changes substantially. A Bloom filter is valuable because its strongest answer is no. It saves expensive work by proving where the data is not, then gets out of the way when certainty requires the real system.